In this video, we're going to continue to look at solids of revolution and finding their volume. But we're going to be looking at something called the Washer method. So the Washer method is used when the region that we are rotating around an axis is not bound entirely by the curve and the axis of revolution itself. So you can see for these problems, examples 3 through 5, the region that we're going to be looking at is going to be enclosed by this line here, y equals x, and then the curve y equals x squared. So we have this region here. In the example that we're looking at right now, that region, that enclosed area, is going to be rotated about the x-axis. So if we were to actually take this region and rotate it about the x-axis, we would get a figure that looks like this. Now, the way that this is different from something like we saw in these problems here, where we use the disk method, is in the disk method, these are solid figures. There's no like hole in the middle. If we were to try and pour water in there, it couldn't hold anything. Whereas in this function, or in this solid of revolution, I could basically fill this up because we have an empty space in here, right? Because there's a gap between the curve, the bounded region, and the axis of revolution, there's going to be a gap or a space inside of that solid. So you can imagine us rotating this around the x-axis, and then there's going to be kind of like this open space like inside here. So we could fill that with water or something if it was an actual like vessel that was could hold some matter. And the reason why we call it the Washer method is if we were to take a look at the cross section, so if I were going to take this solid figure and cut a slice right here, our cross section would give us a washer. So we would get something that looks like this. So you can imagine, right? So here is this point, the radius lies on the x-axis, and this length that we have here, right, this longer radius is the distance that we have from this point here to the outside curve, right, or to the upper curve. And then this shorter radius is the distance that we have from here to that inner curve there, that lower curve. And so what happens is we get this kind of a washer shape, which is why we call this a washer method. Now, if we wanted to find the area of this cross section, the area is going to be the area of this bigger circle minus the area of this smaller circle. So if we're going to define our function, we still integrate it's still the integral of a of x dx or a of y dy, depending on whether you're integrating with respect to x or y. And I think one thing that I forgot or neglected to mention in the last video is whenever we're taking our cross sections are always going to be perpendicular to our axis of rotation. So if I'm rotating about the x-axis, right, so my x-axis lies horizontally, then my cross sections are going to be vertical. And so that's going to be one thing that's important. And you are going to integrate with respect to the variable that your axis of rotation is parallel to. So in this case, we're rotating about the x-axis, so we're integrating with respect to x. So we still are going to integrate a of x with respect to x, but I need to come up with the function for a of x, right? Because that's still just the area of our cross section. So what is this function going to look like? Well, the overall area, if we didn't have this punch, is going to be pi times the measure of the outer radius, that length squared. And from that, we're going to subtract the area of this inner circle. So we'll just call this, say, pi times the inner radius squared, right? So I'm going to give a couple names to these. I'm going to call this length of this outer radius, big R, and then the length of the inner radius, little r, because the big R is larger and the little r is smaller. So what that tells me then is that a of x, the area function, is going to be pi big R squared minus pi times little r squared. And we can actually simplify this a little bit and factor out the pi that they have in common. And we can just say that it's pi times the big radius squared minus the little radius squared. And this is going to be a kind of generalized equation for what we would use when we're finding the area using washer method. And so if you have a cross-section that has this washer shape, it's just going to be pi times your bigger radius squared minus your smaller radius squared. So in this situation, what does that look like? So what is a of x? So a of x is going to be pi times. So what is the length of my bigger radius? So the distance from the x-axis to this curve is just going to be the y value of this curve, and that's just going to be x, right? Because again, we're integrating with respect to x here. So it's going to be the value of x, right? Y equals x, and then squared. So that's the length of big R. The length of little r is the distance from some x value to this curve here. And we know the y value is just going to be whatever that height is. And the y value is defined by x squared. So it's going to be x squared, this quantity squared. So then a of x is going to be pi times x squared minus x to the fourth. And we are going to integrate this function. So it's integral. So we're integrating with respect to x. So we're going like this, right? Those are what our slices, our cross sections are going to look like. We're going from 0 to 1 of pi times x squared minus x to the fourth. And then all of this with respect to x. So just like we did in the past, we can factor out pi because it's a constant. So it's pi times the integral from 0 to 1 of x squared minus x to the fourth. And take the antiderivative of this. So doing the antiderivative of this is going to give me pi times x cubed over 3 minus x to the fifth over 5. And this is evaluated from 0 to 1. So let's go ahead and evaluate this. So we're going to get pi times, so plugging in 1, that's going to give me 1/3 minus 1/5. 1/3 minus 1/5. And then all of this minus, plugging in 0, that's going to give me 0 minus 0, which is 0. Sorry, 0 here. And getting a common denominator and putting everything together, common denominator would be 15. So that's 5 fifteenths, and that's 3 fifteenths. So 5 minus 3 is 2 fifteenths times pi. So it'd be 2 pi over 15 cubic units. And that would be the volume of this figure here. So the key to this is really figuring out what the value of r, big R and little r is, and then remembering to square it and multiplying the difference of those quantities by pi. And that's what we're going to integrate here. So what happens if, so we're dealing with that same region. Remember, we're dealing with the same region here. It's y equals x and y equals x squared. So what happens if, so we have y equals x here, and then we have the y equals x squared region here. But now, instead of rotating about the x-axis or the y-axis, we're going to rotate about some other horizontal line. So this horizontal line is the line y equals 2. So if I'm making a big gap between my curve and my axis of rotation. So you can see, right, there's going to be these big, there's these big spaces, and there's now like a hole in the bottom of this. So if I try to fill it with water, we'd have water that kind of just pours out the bottom here. So it's kind of like a funnel shape. So what would be my area function? So again, I want to define a of x. So what is a of x? We're integrating with respect to x because we have a horizontal axis of rotation. So we're going to take cross sections that are perpendicular to it, and that's going to be integrating with respect to x. So it's going to be pi times, we need to find out what big R is, and we need to find out what little r is. So big R is just the distance from, so big R is always just your longest distance. So if we were looking at this point here, the distance from that point to this bottom edge of the curve is going to be the longest distance. So what is that length? Well, this kind of goes back to what we looked at when we were talking about area but under a curve, right? So to find the distance, it's always the top minus the bottom, and that's what's going to give us the longest length. So the top value here is 2, and the bottom value is x squared. So big R is going to be 2 minus x squared. So that's big R. Little r, I'll kind of show it up here, is the distance from here to this inside curve. They'll call that little r. And little r then is going to be 2 minus, this function here has a y value of x. So it's going to be this. So if this is big R and that's little r, so we know that it's going to be big R squared minus little r squared. All of that times pi. And this is my area function. And if we wanted to clean this up, because we're going to have to, we know we're going to have to take the antiderivative of this, what are we going to get? So if you expanded all of this out and you did that algebra, we would get, this is going to give us 4 minus 4x squared plus x to the 4th, and then this is going to give us 4 minus 4x plus x squared. And if you combine all your like terms, what you're going to get, and you put it in standard form, you're going to get x to the 4th. You're going to have 5x squareds that are negative, because don't forget you're also distributing this negative through. And then you're going to have a plus 4x, because the 4 here and the 4 here will cancel when you squared. And this is going to be the area of our cross-section. So that's the area of a cross-section. You can also see these expressions here, these values of r and little r. So big R is, big R is this distance here, right? The distance from our axis of rotation to the outer ring. And then little r is the distance from our axis of rotation to the little inner ring there. So that's little r. Okay. And then you would go through and integrate this. So it's going to be the integral of pi times all of this, x to the 4th minus 5x squared plus 4x integrated with respect to x. Now, in this case, where are we integrating from? So remember, we're still doing these like vertical slices, right? So we're still doing these vertical slices like this. So our limits of integration actually hasn't changed, right? We're still going from 0 to this point here, which is there at x equals 1. So our limits of integration are still from 0 to 1. So we can pull out the pi here. So I'm actually just going to do that now. We can pull out the pi here. And if we take the antiderivative of this, it's going to be pi times, so that's going to be x to the 5th over 5. That's going to be minus 5x cubed over 3. And then this is going to be 4x squared over 2, so that's going to be just 2x squared. And this is evaluated from 0 to 1. When I plug in 0 to all of these, the 0 is going to cancel out, so it's just going to be whatever I get when I plug in 1. So this is going to be pi times, plugging in 1, it's 1/5 minus 5/3 plus 2. And then again, if I plug in 0, it's going to be 0. Doing all the arithmetic and combining all your terms here, we're going to get 8 pi over 15. So it's going to be 8 pi over 15 cubic units for the volume of this region here. Okay. So let's look at one more example on the washer method. So in this last example for washer method, we now have, so here's my y-axis, here's my x-axis. It's the same region, right? This is y equals x. This is y equals x squared here, that function. Except this time we have a vertical axis of rotation, and it's to the left of the y-axis. So if we have a vertical axis of rotation, that means we're taking horizontal slices. So we're basically stacking volume upward, which means we're going to be integrating with respect to y. And integrating with respect to y means we have to solve these equations for x. So y equals x, it's going to be x equals y. So that's what they've done here, right? So they solve that for us there. And then y equals x squared. We need to solve for x by taking the square root. And so that's what they have done for us there. So now we want to figure out what a of y is, because we're integrating with respect to y here. So it's still pi times the bigger radius squared minus the smaller radius squared. We just have to figure out what big R and little r will be. Okay, so big R. So it's the distance from here to the outer curve. So remember, you do right minus left here. So the right is the square root of y. So it's the square root of y minus a -1. So it's going to be plus 1. That is going to be squared. And then minus the distance from our axis of rotation to the inner ring. So it's going to be, in this case, y minus a -1. So it's going to be y plus 1. And then this quantity squared here. And so that's what gives us this distance here as big R. And then this distance here is little r. And then they're just showing this as a length of 1, right? It's showing it's 1 unit away. So that's another way you can think about it is we know that the distance from like here to here would be the x value, and then you're just adding 1 to that x value, and the x value is represented by those functions there. Okay, so if you do the algebra and you expand all this, what do you end up with? So we get that a of y is going to be pi times, so I'm just going to do the expansion. So it's going to be 2y, 2 rad y minus y squared. And I'm going to want to rewrite this with a rational exponent. So it's going to be pi times 2y to the 1/2 power minus y squared. So this is what you get as a result of squaring all the stuff, combining like terms and such. So let's go ahead and do the integral here. So we're doing horizontal cross sections now, right? So we're kind of slicing this way. So the lowest value is going to be 0, and then the highest value, right? So up here, we're still actually at a y value of 1, but this time we're looking at the y values. So it's going to be pi times the integral from 0 to 1. I just pulled the pi out ahead of time because I know that it's a constant that I can do that. So it's pi times the integral from 0 to 1 of 2y to the 1/2 minus y squared, integrating with respect to y here. All right, so let's do the antiderivative. So it's going to be pi times, so you add 1 to the exponent, so that's going to be 3/2, and you divide by 3/2, which is the same as multiplying by 2/3. So 2/3 times 2, that's 4/3, y to the 3/2, minus, this is going to be y squared over 2, and then minus y cubed over 3, evaluated from 0 to 1. So we've been pretty lucky in all these that our lower limit of integration is 0, because that kind of just zeroes all of that stuff out. So we just plug in the upper limit, and we're going to be subtracting 0 from that value. Okay, so plugging in 1. 1 to the 3/2 is 1, times 4/3 is 4/3. 1 squared over 2 is 1/2. 1 cubed over 3 is 1/3. So that's plugging in my upper limit of integration. Plugging in 0 to all of these is going to make it 0. And we get that. So when we combine all of our like terms, what do we get? So 4/3 minus a third, well, that's just 1. 1 minus a half is a half. So we end up with pi over 2. So we get pi over 2 cubic units for this example.